Hello everyone, welcome back to Math 221. As promised at the end of last week, we're going to turn our attention back to these exponential functions and hit them over the head with some calculus. Okay, so let's start with our good friend e to the x. Okay, we'll look at logarithms and exponentials with other bases in the next part. But for right now, we'll just look at e to the x. If we want to calculate the derivative, we can go back to our limit definition. We're going to get e to the x plus h minus e to the x over h. Okay? And we can use our exponential rules here, right, to write this as e to the x, e to the h, minus e to the x over h. And then, making sure we're writing this limit as h goes to 0 every time, we can factor out this e to the x, e to the h minus 1 over h. And then since this e to the x has nothing to do with h, we can actually bring it out front. And then we're left with this, as h goes to 0, of e to the h minus 1 over h. And working this out explicitly is beyond the scope of our course. If you were to go in and plug in some values, maybe 0.1, negative 0.01, you'll see that this expression, this goes to 1, okay, as h goes to 0, which means that f prime of x is just e to the x, right? This is why everyone cares about e to the x so much, because it is its own derivative. It's in fact the only function that is its own derivative. Of course, something like, g of x equals 3e to the x, well then g prime of x is 3e to the x, right? If you stick some constant out front here, you're still gonna, keep this property of it is its own derivative. But e to the x defines this class of functions, right, where it's its own derivative, which is incredibly important. We can do some examples of just, calculating the derivative. Okay, let's start with, let's say x squared e to the x, right? If we're wanting to calculate the derivative, right, first we need to obviously take the derivative of this whole thing, but that's going to be the product rule, right? It's going to be x squared times d dx of e to the x plus e to the x times d dx of x squared. And then we can run through these. As we said, the derivative of e to the x is itself, so we just get e to the x. And then the derivative of x squared is going to be 2x, so we have e to the x times 2x. But we can factor this guy, right? Each of these has an e to the x and has a factor of x. Then this one here is left over with 1x. This one here is just left over with 2. So we get e to the x times x, all times x plus 2. Next, we can take a look at something like this. Say g of t is e to the t plus 2 all to the 3 halves. right? This is going to be the chain rule. So we can do this chain rule in its entirety. Set u equal to e of t plus 2. Then u prime, well, the derivative of e of t is, or e to the t is itself, right? And the derivative of 2 is just 0. So this is just e to the t. But that means that g of u is just u to the 3/2, right? So then g prime of u is going to be 3/2 times u to the 3/2 minus 1, or 1/2, right? And then we know to find g prime of t, I need to multiply these two together. So then g prime of t is 3/2 times whatever we called u, which is e to the t plus 2, to the 1/2, all times e to the t. Okay, and you could absolutely, grab your e to the t and bring it out front, as long as it's clear that your t is an exponent. Okay. And so next, of course, the question is, what happens when you have a little bit more complicated of a function, right? What about, say, h of x equals e to the f of x, right? What if you stick some function up here, right? Say e to the x squared minus 2x. Well, there's a couple of different ways to approach this. You could factor this exponent, right, into e to the x times, or e to the x times x minus 2, right, something like this. And then use exponent laws to separate this into two functions and then do the product rule. That could work, or we can do the chain rule to this whole thing. What if we let, say, g equal e to the x, right? Then h of x is equal to g of f of x, right? F composed into g. But we know how to find our derivative here, right? This is going to be g prime of f of x times f prime of x, right? But then we know g of x, and f of x is just some function. So that means that h prime of x is going to be g prime of x, but g prime of x is just g of x, right? So this is just going to be e to the f of x times f prime of x, right? So rather than breaking this up, we can solve it much simpler, right? We can write this as e to the x squared minus 2 times 2x minus 2, just taking the derivative of the thing that's in the exponent. We can do a handful of examples kind of from here. Once again, computing the derivative of the following. So let's just start with something nice and simple. Say y is e to the minus 3x, right? Nice and simple. If we want to calculate the derivative, then we're looking for dy dx. Well, what's this going to be? Well, as we saw on the previous page, this is going to be e to the negative 3x times d dx with minus 3x. But the derivative of minus 3x is just minus 3. So we're left with minus 3 e to the minus 3x. Right, we can grab something with a little bit more meat to it. Say f of x equals e to the x cubed plus 4x squared minus 3, right? This is going to follow the same pattern, right? F prime of x, well, it's e to the stuff, because the derivative of e to the x is just itself. And then we need to multiply by the derivative of that stuff, x cubed plus 4x squared minus 3. But then, we can copy all this. What's the derivative of this inside? Looks to me like it's going to be 3x squared as the first one, and then plus 8x. And then this 3 just goes away. And that's our derivative, okay? We can also, throw in a product rule with this, right? Say y is x e to the minus 2x. When we do this, right, we're looking for dy dx. Once again, we're going to have x times the derivative, e to the minus 2x because we're looking to use the product rule, plus e to the minus 2x times d dx of x. Then from here, what's our derivative of e to the minus 2x? Well, we're going to get e to the minus 2x times my derivative of minus 2x. Then we're going to add to that, well, the derivative of x is just 1, so e to the minus 2x. Then from here, as we continue simplifying, xe to the minus 2x. The derivative of minus 2x is just going to be minus 2. So I suppose I'll just move our equal sign a little bit. And then we're adding to that e to the minus 2x. And I can factor this, right? Factor e to the minus 2x and get 1 minus 2x on the inside there. Continuing to take a look at these, right? We could do something like, say g of x is e to the t over e to the t plus e to the minus t. And this may seem a little bit convoluted, but expressions like this do actually come up in mathematics a lot, surprisingly enough. So it pays well, to be able to compute their derivatives. This is going to be a quotient rule, right? So we're going to have low d high d dt of e to the t minus high d low e to the t minus, or plus e to the minus t, all over e to the t plus e to the minus t squared, okay? And then from here, we want to slowly start to simplify. Right here, it looks like we're going to have e to the t plus e to the minus t, all times e to the t. And that's going to be minus e to the t. And then that derivative looks like it's going to be e to the t. The derivative of this guy, we're going to get e to the minus t. And then this negative 1 is going to drop down. So we're going to have minus e to the minus t, okay? All once again over e to the t minus, or plus e to the minus t squared. And then we can simplify this sort of a bit at a time, right? As we distribute in that first e to the t, we're going to get e to the 2t, right? Because when you multiply, you add the exponents. But that means that when we add these, we're going to get plus e to the 0. And then we're going to have minus, once again, e to the 2t, but then plus, right, because minus minus, another e to the 0, all over e to the t plus e to the minus t. But notice e to the 0 equals 1, because anything to the 0 equals 1. So we have 2e to the 0, so 2, plus e to the 2t minus e to the 2t. So this is just 2 over e to the t plus e to the minus t squared. And once again, the quotient rule continues to have this weird habit of looking like it's going to be extraordinarily complicated and then simplifying down really nicely. Now, one of the things that we'll talk about on Thursday is sort of all of the wildly different ways that we can use exponentials when we're building mathematical models. Okay, and one of the most common situations or models that we'll see is something like this. Q of t is q naught of t e to the kt. Okay, and depending on the model, right, q might be called something different, k might be called something different, right? In this case, q0 and k are constants, right, that sort of describe your situation. This one in particular models exponential growth, but all throughout different disciplines, you'll see functions just like this. Okay, but let's say we wanted to calculate its derivative with respect to time. How would we want to do that? Well, our q naught is going to just sort of fall through because it's a constant. Our e to the kt falls through, and then we're left with d dt of k times t. But remember, k is just a constant, right? T is our actual variable. So this is q naught e to the kt times k. Or I'm actually going to write it with the k out front, q naught e to the kt, because what I want you to notice is that this quantity here, this is q of t. So what that means, right, this is one of the really nice properties of exponentials in general, is that the rate of change of q of t is directly proportional, right, to its value with some proportionality constant k, right? That's what makes calculus so useful for these situations, because it shows us this, right? You're wondering how fast q of t is changing? We'll multiply it by this constant factor k, and it just spits it out towards you right away. And of course, we can do other things with these, right? We can graph them, or we can say look for in inflection points, right? So let's say find the inflection points of, say, f of x was e to the minus x squared. And using the tools from last week, we could absolutely graph this after. But in this case, we'll just go through the calculus to find these inflection points, and I'll show you a graph of it when we're done. But in order to find the inflection points, right, we need to take the second derivative. But in order to take the second derivative, well, we need to take the first derivative, right? So here's our first derivative. We're going to have e to the minus x squared times d dx of minus x squared, which looks like it's going to be minus 2x e to the minus x squared. For our second derivative, now we're going to have to use the product rule. Minus 2x times d dx minus x squared, okay, plus e to the minus x squared times my derivative of minus 2x. We already know this should be e to the minus x squared. Sorry about that. We already know its derivative because we calculated it here. So it's going to be minus 2x e to the minus x squared. And then we're going to add to that e to the minus 2x. The derivative of minus 2x is simply minus 2. This first term looks like it's going to be 4x squared e to the minus x squared. Then minus 2 e to the minus 2x. And it will actually be easier if we factor this, okay? So e to the minus x squared, you can actually factor out a 2 times e to the minus x squared times 2x squared minus 1, okay? And remember that to find our points of inflection, we need to use the sign diagram, and we need to find where this function equals 0. Okay, I'm actually going to go on to the next page. Our second derivative was 2e to the minus x squared times 2x squared minus 1. And we need to find where that equals 0. Okay, so what values of x has this equal to 0? Well, notice this guy is never going to be equal to 0, right? Because e to the something is always greater than 0. So that means that if this were to equal 0, then this would have to be equal to 0, right? 2x squared minus 1 equals 0, which means that x squared is what? 1/2. So x is 1 over the square root of 2. And that's actually plus or minus 1 over the square root of 2, right? Because we're taking square roots here. And now, of course, we do need a sign diagram. Right, so we'll have minus 1 over the square root of 2 here, and we'll have plus 1 over the square root of 2 here. If we plug 0 into this, e to the 0 is going to be 1, so we have 2 on the outside, times a minus 1, right, because this term drops. So this is going to be negative in here. And then it would seem to me like the easiest things to choose for here and here would be to just choose 1. Well, as we said, if we choose 1, this guy's always positive, right? And then this one is going to be 2 times 1 squared minus 1, so also positive. And a positive times a positive is a positive. And then actually, funnily enough, the same thing happens here. Right? This term is always positive no matter what we throw in for x. And then this term is going to be positive as well, because that negative 1 is going to become a positive 1 when we square it. So that means that these 2 points here are our points of inflection. Okay? And we should find out what their value are, right? So what's f of, say, 1 over the square root of 2? Well, that's e to the minus 1 over the square root of 2 squared. which looks to me like it's going to come out to e to the minus 1/2. And indeed, just as we had happening here, when I put in minus the 1 over the square root of 2, this squared is going to get rid of it, and we're going to get the same thing. Okay, so my points of inflection are 1 over the square root of 2, comma, e to the minus 1/2, and minus 1 over the square root of 2, e to the minus 1/2, okay? And if you were to go through the trouble of graphing this guy, evidently it doesn't want to, there we go. If you were to go through the trouble of graphing this guy, that's closer to centered. It's going to look a little something like this, okay? Where your points of inflection are there and there. A fun fact about this graph that, I mean, I think it's kind of cool. Maybe you'll think it's cool, maybe you won't. If you were to take all of this area under the graph, right, all of this, if you were to find some way, and we'll talk about some ways to do this here in a couple weeks, to add up all of this area, you actually get the square root of pi for that area, which is kind of cool. It's always fun to find connections between e and pi. There are more than you think, but unfortunately, even though as I said, I think it's very interesting. It's well beyond the scope of this course, but it is a little fun fact that if you add up all of that area, you get the square root of pi. We'll do one more quick example. So say you're working with some piece of real estate, right? And the market value of it is governed by this equation, right? You build your fancy model builder, and it spits out that it's 300,000 times e to the minus 0.09 t plus 1/2 times the square root of t, for t is between 0 and 10, okay? And you're interested in finding the optimal value of this, right? You're trying to sell it, so you want to maximize the value, right? And so it asks the question of, well, how do we optimize the function? Well, we studied this in depth last week. And so that would mean that, well, we should take the derivative and then look at its critical points and then compare that to those on the boundary, right? Well, in order to do that, we are going to, in order to do that, we're going to need to take a derivative, right? So let's take a look at p prime of t. Well, the 300,000 factors through. My e to the 0.9 t plus 1/2 square root of t doesn't change, right? I'm actually going to go onto the next line. This is multiplied by d dt of the exponent, right? 0.09 t plus 1/2 the square root of t. Well, we know how to take those derivatives, right? We copy the stuff that doesn't change. 0.9 t plus 1/2 the square root of t. If we move this over here, we can probably fit it onto a single line, right? My 0.09 t just becomes a minus 0.09, which I'm actually going to put over here. And then the derivative of this guy is 1/2 times the derivative of the square root of t. So we can do 1/4 and then say t to the negative 1/2. Right? There's a number of different ways to write that. Minus our 0.09. But then, of course, in order to find critical points, we need to set this guy equal to 0. But as we saw in the last one, right, if this is equal to 0, well then this part right here has to be the one equal to 0, because this is always positive, right? And so that means that 1/4 t to the minus 1/2 minus 0.09 equals 0. And we can write this a couple of different ways, right? We can go 1 over 4t to the 1/2 might be an easier way, equals 0.09. But that, of course, means that t squared, or t to the 1/2, sorry, is equal to 1 over 0.09 times 4, or 0.36, right? And then t is equal to the square of that. 1 over 0.36 squared, which is about equal to 7.72. Okay. And then now what we want to do is we want to test these values that we found in P and look for the largest one, right? So we need to check P of 0 years. I suppose I just realized that I forgot to tell you what this actually represents, right? This is years from now, right? We need P of 0, which if you were to plug this in, you would see that this would become 0, and then e to the 0 is just 1. So we're left with 300,000. P of 7.72 years. Well, if you run that through a calculator, you're going to get 600,779. And then P of 10 years is a little bit less at 59,838. And so the winning time to wait is 7.72 years, and that's when this property will be at its highest value for you to sell.